The last thing we wanted to be able to compute about vector fields is, in the context of a vector field that represents a force, we wanted to be able to compute how much work that force does on an object that's moving around. So let's say we have an object that moves along a curve R, where the parameter for the curve goes from A to B, and as it moves, it's being acted upon by a force given by some vector field, capital F. What is the total work that the force does on the object? Now, one thing that we are not assuming that the force is causing the motion of the action, the motion of the object. Okay, the object is moving on rails along some path for some reason, and as it moves, one of the things causing it to move, I guess, is the force, and we're just computing the force, right? If the force from the force field were the only force acting on the object, and we wanted to know what motion that caused, that would give us some differential equations to solve. So that's a different kind of problem. So we are not assuming that the motion of the object is caused by the force. Still, as the object moves, the force does some work, and that's what we want to compute. So if you haven't encountered work before, all we need to know about it is that if an object moves through some displacement, right? Displacement is a vector. If it experiences a force as it moves through some displacement, and the force is constant, then the work is the force dotted with the displacement, right? Both force and displacement are vectors. So work measures how much energy is put into the object by the force. If that collection of words doesn't mean anything, then don't worry about it. So one key thing about this definition is that the force has to be a constant and the displacement has to be straight to use this definition, right? But of course, most force fields aren't constant, and most paths through space are not straight. So to be able to figure out the work done by a force field, by a varying force field on over a non-straight path, things are going to be more complicated. So to figure out what expression we should use, let's imagine we have a path. Now, since we have a path, it's going to be some kind of line integral. The question is, what line integral? What do we integrate? Now, since the force and since this path isn't straight, and since we're not assuming the force is constant, we can't use this expression directly. But one key to calculus is imagining that you can zoom in on a single point closely enough so that anything that was varying doesn't have time to vary, and so is constant, and also so that anything curved appears straight, right? So by zooming in infinitely far, we will have a force that is constant and a displacement that is straight. So if we zoom in on a single point, right, to get to the neighboring point, we have some displacement, right? This is a small chunk of the I guess how large is this displacement, or what is this displacement vector? Well, if we imagine that it takes some infinitely small amount of time to get from one point to the next, right? That would be time. Time has elapsed dt, and we need to multiply that by the velocity to figure out what this displacement is, right? So the displacement is velocity times time, and the velocity, that's r prime. So notice that. So this displacement is r prime times t. Notice that this is actually just dr, right? So this displacement vector is dr, and the force located at this one spot is, well, it's the force field, and we're imagining that we've zoomed in so far that along this entire displacement, this force is constant rather than varying. All right. So now we have a force at this spot and the displacement that we need to move from this spot to the next spot. So the work at this one point is, right now we can use this original definition of work because we have a constant force and a straight displacement. So it's F dot dr. So the total work is, well, we just do a line integral for this. It's the integral from a to b of F dot dr. But that's actually just a flow integral. So it's a little hard to interpret what a flow integral means if you think of the vector field as a velocity field. But if you think of your vector field as a force field, a flow integral just tells you the work done by the force. All right, let's look at a quick example. Let's find the work done by this gravitational force on an object that moves around this path. I believe I have cooked up this path so that one focus of this ellipse is at the origin, which is a realistic situation for an object orbiting just due to gravity. But this particular parameterization is not how an object would actually move because it's not moving at the right speed. So I won't get into why, but it's a fact. So this path is realistic, but this parameterization is not realistic. Okay, so let's see what happens. So we know because we're calculating work, we just need to integrate F dot dr. So we'd better know what r prime is. R prime is minus 5 cosine t, excuse the horrible handwriting. Y prime is 3 cosine t. I made a mistake. This is minus 5 sine t. There we go. Okay, so there's r prime. Now we can integrate. To go once around this path, we need to go from 0 to 2 pi. We're going to integrate F dot r prime. So F is this whole mass. So 1 over, remember, we need to plug in our parametric curve in here for x and y. Well, x squared plus y squared, oh, that's not going to be something nice, is it? I think I painted myself into a corner by trying to produce a clever example where we have an ellipse instead of just a circle. Let's make things easy on ourselves and just have a circle. So I'm going to scratch out this stuff. So our curve is just going to be a circle around the origin. So that means that this 5 is gone, this 3 is gone. Now when we plug in our parametric curve, x squared plus y squared is sine squared plus cosine squared. That's 1. Okay, and then the rest of our force field is minus x, so minus cosine, comma, minus y, so minus sine, okay, and then dot that with r prime, so that's going to be minus sine t, comma, cosine t dt. All right. So integral from 0 to 2 pi of the scalar in front is just 1. So work out our dot product. We get minus cosine times sine. So that's sine t times cosine t. And plus, and then minus sine t times cosine t, minus sine t times cosine t. Well, look, that's going to be 0. Right. So when we have something at the origin gravitating and an object that moves around a circle, the force of gravity does no work. It does no work on this object. In fact, the total work around any orbit would be 0, but the integral would be much harder if we kept the original example.